Hello, good morning, good afternoon, and good evening, wherever you may be. Welcome to today's webinar hosted by ASE Kalkitech. I'm Midun from the marketing team at ASE Kalkitech, leaders in grid communication solutions. Today, we are going to discuss about how to verify IEC61850 models in the network using SCD files. We'll be giving you a brief understanding about how to verify IEDs using SCD, both in client mode as well as listen or monitor mode. We will be extensively showcasing this using our latest version of our product, the ASE61850 Test Set. As regular attendees to our webinar may be aware, this is going to be a listen-only webinar. If you would like to ask any questions or have any queries, please feel free to ask them in the chat screen. I will consolidate all the questions and have it answered towards the end of this webinar. If in case we are not able to answer every question due to lack of time, we'll get in touch with you personally and address all your queries over email. This is going to be a 45-minute session. Hopefully you'll be able to finish it within the time, and will be followed by a 5 to 10-minute Q&A as well. A recording of this webinar will be sent to all attendees after 24 hours. You should also be getting a webinar certification, participation e-certificate in a separate mail. Now, without further ado, let me introduce the host for today's session, Sterren Jose. Sterren's focus at Applied Systems Engineering of Calcitech is in the product management of IEC61850 tools and project management of ACDR integration projects. He has over 20 years of experience in the design and development of grid communication products and tools, in addition to project management expertise. He's been an instructor for numerous technical courses related to grid communication protocols, of course 61850 and also ICCP. Sterren has also published and presented numerous white papers around grid communication protocols, most recently at Pacworld US, and has been, of course, a regular visitor to many of the other technical committees as well. Great. So I see the people have come in. I think we can start. Sterren, over to you.
Yeah, thanks for the introduction, Vidhan. Yeah, to give a quick overview of the ASE61850 test set, those who are not familiar with the tool. At Applied Systems Engineering, we have been building test sets from very beginning, and ASE2000 is our flagship product, which covers all the legacy protocols, TNP3, IEC, and Modbus, and other protocols. And we are adding DER protocols also into ASE2000 now. And on the other side, ASE61850 test set is capable of doing client server and monitor mode features. We support Exchange framework for test automation in all the modes, and with the support of sampled value and process bus simulation, we are kind of adding our capability or extended our capability beyond MMS and GOOSE. So that will be done using BNET hardware. I'll be showing the pictures and details of the BNET in this demo very soon. And in 2.3.0 release, we have a new feature, as Midun specified earlier. We have Verify IED feature, and we will be focusing more on that feature during this webinar. And to give a quick overview of BNET with sampled value support, we have support of IEC 61869-9 up to 24 channels with the 2 ASDU capability with all PTP profile support. And we also identifies RMS angle changes, missing of packets, and delays in the network. So kind of a comprehensive sampled value simulator and testing tool for the process bus. Giving further introduction to ASE61850, we support it on Windows-based platforms, and currently licensing is done using the dongle. We also have the server-based license for the software, and software will also work with the ASE2000 license. And regarding the BNET hardware, we have 4 physical network ports, 2 Ethernet and 2 fiber optic or Ethernet. These two ports can be changed to Ethernet if you have the corresponding SFP adapters. And we support sample to value simulation and testing. As I mentioned earlier, we have several LEDs for indicating the status of publishing and subscription and errors. Today we'll be focusing on verify IED feature in client mode and monitor mode. I'll be providing the details of how the test setup is, how we'll be presenting the details that we will cover in a separate slide. And other 2.3.0 improvements are mostly around sample to value capability. Other than the verify IED feature in client and monitor mode, we have IEC61850 support extended and several PTP profiles like C37 power profiles and utility power profile available in BNET now to synchronize with the external clocks. And we also have a capability to delay and advance the SV publishing so that user can kind of find out how the relays are behaving in the case of unsynchronized or not synchronized merging unit scenarios. Proceeding with the verify IED test setup, we have three kind of entities here. In the first demo, we will focus on client and server scenario, where we will have two IEDs, one with the proper matching SCD scenario, and the second one will be like mismatching scenario. So in the mismatching scenario, we will simulate a case where um, there are some changes between the client and server. So in this case, the use case we are trying to achieve is if the IED is deployed with a slightly different data model and data sets, how the client can detect by querying the device and how quickly it can do that. So that part we will be covered in the first demo. And in the second demo, we will cover how a um, monitoring system, basically the test set, can also act as a monitor. So if the IED and HMI or SCADA is already communicating um, each other, and how a monitoring device can detect any changes from the SCD. So in this case, we will have both client and server running with same modified SCD file, and the monitor mode will have the original file. So that means monitor mode will be expecting certain data points in client and server, and it will look at the report and GOOSE to verify that. So we'll see these two use cases today. And to identify the use cases, we have simulated a scenario where one of the logical node is missing in one device, LPIU. So we will be simulating LPIU in the test set as a server side. So we'll be removing this XCBR13 from LPIU. In that case, what will happen is the corresponding data elements will be missing from two data sets, and one of the data set is used in GOOSE. So that means the GOOSE which are published in the network will have some elements missing, and the reports, if once enabled, will have some elements missing. So that is the use case we are trying to showcase here. And in client mode, we'll focus on the data model and datasets checking, where client will query the data model from the device, and it should be able to detect the um, errors in the device where the XCBR13 is missing, and it will also check for the dataset integrity, and it will find that the certain elements are missing in datasets as well. So that's the scenario in client mode. And in monitor mode, we will look at the reports and GOOSE which are already exchanged between client and server, and it will highlight the differences in the report and GOOSE. So these are the two use cases. Okay, so going back to our test setup, I'll be demonstrating this with a laptop. I don't have a real device with me, and hence I'll be simulating these two devices. LPU will have matching data model, and LPIU is the one without matching data model. So let me quickly set up the server. To easily find out the details, I will show the original project where you will be able to see the actual data model of the device. So that means it will kind of display the details of the actual device. So let us go to the LPIU, and here if you browse to the logical node and browse to the last logical device, you will see that XCBR13 is present in this device. So this is the logical node that we are going to remove in the simulation scenario. And coming to the data set, we will be focusing on two data sets. This data set currently has the XCBR13 elements, the position of the breaker and other elements. And in the simulation, we will remove those. Similarly, we have another data set which is assigned to the report. And here also you can see the XCBR13 elements, right? So this is the original file that we will load in the client side. And in the server side, we will load a modified SCD file with those XCBR13 removed. So I'll open that project and show you that file. So here you can see that this is the modified project where we don't have the XCBR13. So here you can see that this is a modified file where XCBR13 is missing. So I have exported both these files here. So if you look at the details, so here we have the original file and this is the modified file. So for this scenario, we will start the test set. And in test set, we will load, in server mode, we will load the modified file. So basically we are trying to kind of simulate the scenario where device is deployed with some of the mismatches, like it is not complying to the SCD file generated. So we'll switch to the server mode. And before going to that, I will show the IP addresses available on this computer. So here we have certain IP addresses configured. So we'll be focusing on the IP addresses available under 20.series. So we'll be simulating devices with these IPs. So to simulate server, you will need the IP addresses available as alias IPs on your computer. So I'll select the modified SCD file and I can just show you the path from where I'm browsing the file. So here we have the folder, and here I'll be picking up the modified file from here. It will list down all the devices in that file, and you can pick the devices that you want to simulate. So in this use case, we will focus on LPIU with the data model mismatch and LPU without any data model mismatch. So these are the two devices that we are trying to simulate. So once the IP addresses are assigned, you may start we'll start the device and we will kind of show you the details here. Going back to the file. Okay, I've selected the file. Okay, so now going back to the data model, I will explain it here. The goose that we are trying to simulate is here. you'll see that the goose elements, sorry, I think it's the second goose that we are trying to simulate. Yeah, this one. So here you will see that the XCBR13 elements are missing here. Okay, let us also look at the report. So here, if we look at the report, you can see that XCBR13 elements are missing. Okay, so we'll keep this running. Right now the goose is being simulated, and reports will be generated once the client connects to the device and enable it. So let us run this system, and now I will go back to the other computer where we will be simulating the client. Okay, so I'll copy the file. Yeah, this is the file that we are trying to simulate. So I'll browse the file here. So here I will pick the original file. So that means client is running with the original file, and device is running with the modified file. So that's the use case. So I'll specify the same IP address here. So client is connected to the device, and it is showing the, at this point it has not verified anything, so it will display the details here. So here, if you look at the goose, you will notice that XCBR13 is present from the client perspective, right? And if you go to the reports, you will see that it has the XCBR13 elements, and these elements are XCBR13 is present in the logical device as well. So that means the client is expecting this logical node to be present. Now let us do the verify IED scenario. So to use the exchanges, basically you drag and drop elements from the tree to the respective exchanges. We have several exchanges to simulate connect, read, write, validate, to verify reports and enable reports, goes control, etc. So this is the newest addition into the list. We have verify IED here to automate. You will be able to do this periodically also, say once in a day or something, if you want to continuously um, verify, like make sure that if there are no changes done in the device, you will be able to sequence this forever. So as soon as any uh, modifications are detected, you will be able to identify those. Okay, I have dragged the device here, and I will go ahead and run the verification process. And before that, I will expand this for a better viewing. So here we'll focus on the data sets and logical node. Yeah, these are the elements that we are trying to test. So it will start. Okay, so you can see that device has verified. So if you collapse everything, you will be able to trace the changes. Basically, you can see that there are some changes in the logical devices detected by the tool, and you can see that 2 of the 3 logical devices are good. You'll be able to see a tick mark there. And further, if you expand the logical device with errors, you can see that XCBR has the error. And if you expand further, so there could be a case where some of the data elements are missing so in those cases, we will do a cross mark and indicate that it is not present. But in this case, XCBR itself is not present. That's why you will see all elements under XCBRs have the warning sign. So this is the way to identify whether there is any mismatches in the data model part. And if you browse to the data set, you can see that here, instead of a tick mark, you are seeing a warning sign, which means there are some errors in the data set as well. If you collapse all the data sets, you will see that some of the data sets have the problems. If you expand further, you will see that which data elements are actually missing. So here you can see that POS eval from XCBR13 is not present, and similarly there are other elements which are not present. If you go to the other data set, you will see that the POS element from XCBR13 and operation count from XCBR13 are missing. So this will give you kind of a scenario where you can easily identify by tracing the tree node. You can find out where you will see the errors in the data model. The next version, we will extend this further to other parameters, like we will cross-check buffered report and unbuffered report and GOOSE parameters and verify those as part of the client verifications. That feature is currently not available, and it will be available in the next version. Now we will go to the second scenario where, let us go back to the presentation where, so we saw that data model is identified by the client, and dataset element missing scenario also is identified. Now let us go back to the monitor mode where client and server are running with same model, which is modified file, and monitor mode or the monitoring device is running with a different original SCD file. So we'll see how the monitoring device will be able to detect the report and GOOSE. So for this use case, I'll remove the current file. And I'll run the modified file. So just to make sure that I'm using the right file, I'll select it from this folder. So now I am setting up the client. Okay, so client is set up with the matching model as in the device. So once that is selected, so now we are in client simulation, and if you browse to the GOOSE dataset, you'll see that XCBR13 is missing in client as well, because we have loaded the SCD file which is matching with the device. So that's why you don't see XCBR13 here. And if you browse to the buffered reports and go to the data set, you will see that XCBR12 is missing here. So that's the so now device and HMI or test client has matching configuration, and you will be able to see that the GOOSE is being received in the client. And to enable the report, we will browse to the report control block section, buffered reports, and now you can see that it is not enabled. That's why it is not sending any reports. So we'll make sure that the trigger options is set with the integrity. We can also see that the integrity period is a very high value, which is 10 minutes, 600 seconds actually. So we'll reduce this to 10 seconds so that we will be able to quickly finish the demo. So I have changed the integrity period in client. This is returned to the server right now, and I will go ahead and enable the report. So expectation is that in every 10 seconds, a new integrity report will be generated from the device and sent to the client. So now we can see that both reports and GOOSE are coming. GOOSE will be displayed, new GOOSE entries will be displayed only if there is any state change detected by the test set. Now there are no changes in the IED, so that's why we don't see any new entries. But integrity report, due to integrity report, we will see that values are getting refreshed. And if you select the data point column, you will be able to see the list of data points in that goose. Similarly, if you do the same for goose, you'll be able to see all the goose elements here. So if you want to kind of quickly review the values coming from the device, this is an easy way to find out. Okay, now the client is set up and server is already running. Now let us simulate the monitor mode. I don't have another computer, so I'll simulate the monitor mode also in the same computer. It doesn't matter, because as long as you have the connection and network traffic visibility to the computer, the monitor mode will work. So you may run it in a different computer or same computer, that doesn't matter. So in a real use case, you will be running it on a different computer, mostly with a mirror port connection to the switch, so that you can see all the traffic. So by default, when you start, the tool will be started in client simulation mode. You'll have to go to this T button to enable the monitor mode. Once the monitor mode is enabled, it will by default go to the messages pane, and let us select the original file. So in this case, the use case we are trying to demonstrate is that monitor mode has the original file and client and server are running with a different configuration. So our objective is to verify that monitoring device or test device will be able to detect the changes. So you'll still have to set up the monitor mode device. Okay. When you are in monitor mode, it cannot make any connection to the device through MMS, or it can only listen to the traffic. So now you can see that there is some read request going back and forth between the device and the client. You can look at that quickly. Yeah, it is, since we have selected the report parameter here, it is issuing a read, periodic read. Once we change the selection to some other node, it should stop doing that. So now, yeah, now we should not see any traffic between client and server. So you can see that it just stopped. Now let us do the verification part. So browse to the device and drag and drop to the verify IED exchange. So here, let us expand the reports and goose. Okay. So our expectation is that the report, which has the data set, it has got 13, XCBR 13. So this monitoring device will be expecting XCBR 13. And from goose perspective, also we will be expecting XCBR 13 related elements, which are not present in the client and server. So if you want to trigger the exchange only once, you'll be using this fourth button or once button. Let us run that. So I'll collapse the details here. Okay. So the tool will look for the integrity period in the case of reports, and for the goose, it will wait till the maximum retransmission time. So it will wait till any reports are goose being received, and based on that, it will flag the entries. So let us run the verify IED feature. So it has started. So it will have to wait till it receives any goose packet or report packet. Let's see. Yeah. So it was waiting till the maximum retransmission time, and it also waited till waited till any reports arrived in the port. So here you can see that it detected the 3 goose mismatches. So here you can see that it could not get these goose messages, and it also received this report, but it found that there is data point not found in remote device. So here you can see that it is missing, and here if you see the data point not found in remote device, so you'll find the errors here. And based on the actual scenario where all the reports are subscribed by some clients, some test clients, or if goose are being published in the network, then you will be able to see those scenarios here. You will see a tick mark if any reports are coming with the matching data set. So you can verify that here. So this is how the user interface will look like in the current version, and next version we will um, add the dataset view under this reports. So right now dataset is at the top, so that's the reason why you're not able to see the details of the report with the missing data points. So in the next version we will extend this capability to display the dataset elements under the report itself, and same with goose. So you'll be able to view the details in a granular fashion. But yeah, right now you can do a quick verification of the device by using this capability. So next we will focus on other feature where the BNET has a capability to delay or advance the simulation. So typically you will see all the merging units sending data at a normal rate. Based on the PTP synchronization, all the publishers will be sending signals, and the devices or relays will be expecting these sampled values to reach their port within that interval. So how will you find out the behavior of the device when there is a network delay, or when there is a um, some kind of anomalies in the network where some devices could not get the PTP signal properly, and if they are out of sync. So we can simulate those delayed packets or advancing packets, like if in some cases you will have some totally out of time stamped devices. So we will have two scenarios demonstrated. uh, One is we can see how we can find out the delays in the network. Like in the test one, we will physically loop back, physically connect port C to port D. These are SFP ports, so I'll run a cable from port C to port D, and we can check the delays. And we can further extend the network to a switch. So that means I have a switch here. So we'll make a connection to the switch, and we can see how the delays are increased through the switch. And further we can make changes in the timing, so that you can see how we can change the traffic based on what we need, like introduce delay or advance the packets. Let us go to the device. Now I will close this simulation. We don't need that anymore. And instead of connecting to the second laptop, I will connect to the BNET. Okay. So to simulate the scenario, we have a 6150 test set running as a SV tester, and we will have BNET connected. So now we'll make this connection. So to connect to a BNET, You can look at the IP address, you can scan the BNET in the network. And if you are not able to, identify the IP address, BNET will automatically find the IP and connect to the device. So right now, if you look at the BNET hardware, the port A, which is used as a maintenance port, it has the IP address 192.168.1.23, and C and D are the ports we have simulated for the sample value. To do both publishing and subscription, you will need the server mode. Okay. So I have switched to the server mode and I'll connect to the BNET, and there you can specify the ports to publish and subscribe. So here I have selected port C and port D. All the active ports will be shown in green with green tick mark, and you can see that the port B is not connected right now. That's why it is showing a black tick mark. Once it is connected, it will show in green. Or physically connected active ports will be shown in green. So right now we are focusing on the sampled value, hence we are not really bothered about the IP addresses on those ports. Okay, I'll browse a file where we can simulate some traffic. I have added the device here. Now expand and go to the sample value grouping, and for this demonstration I will pick the first one, the list. I'll also add the same to the SV monitor. So in this case we are doing a loopback, but if you specifically want to test some merging unit data, you can only focus on this SMA monitor tab. So you can drag and drop whatever SVs you want to monitor, and you'll be able to see the details here. Now let us start the publisher. Okay, you can see that publisher has started. Now we are not really bothered about the values, RMS and angle values. Still, I will specify some of the current values here, and also simulate some angles for those currents. I'll apply the changes here. You can see that it will be applied, and if you go to the monitor mode, select all the SVs that you want to monitor, press the start button, and now you'll see that those values are displayed here. If you go to the publisher and make any changes, you'll be able to see that in the subscriber. So if in a real scenario, when an IED is sending any changes, the RMS, you'll be able to see the details of the RMS here. So you can see that here 1.3 was the previous value and 1.4 is the current value. So that way you can see the values. So coming back to our demonstrations here, you can see that the average delay is fluctuating between 1.8, 1.5. It's mostly in the range of 1.5 to 2.2, around that. You can see that here, like there are some variations here, but overall it is in the range of 1.5 to 2.5. That's what you will see here mostly, right? The average delay as seen by the BNET. Okay, so here BNET will be referring it to its local clock, and now I don't have the PTP synchronization in the test setup, so it is using the local clock to do that. Then a real network, you can do it with the PTP synchronization. Now let us change the network. Right now we are running with the physical loopback, connecting cable from port C to port D. Now let us loop it through the switch and see the difference. I'll physically change the connections. have removed the port D and connected a cable from the switch to port D. Okay. Now let us go back to our scenario. So you can see that the monitor automatically stopped because it detected missing of packets. So yeah, it detected that there are no packets coming from the device, so it stopped automatically. And from a publisher perspective, it is, yeah, I think it has stopped. Yeah, I think we'll stop and start the communication so that it will give some time to change the sequence. Okay, and now we stopped the publisher with the changes in the network. Now let us run the publisher. Now go to the monitor mode, uh, SV monitor option, and run. So in this case, we should be seeing some increased delay as we are looping the traffic through the switch. So here you can see that an additional 2.5, approximately 2.5 to 2 microsecond has been introduced by the switch. So you can see that it's consistently above 4.5 and 5.5 in that range, right? So basically that delay is introduced by the switch, and that's why, if you physically loop back the cable, you'll see a very minimal delay in the range of a couple of microseconds. But if you loop it through switch, the delay is increased further, and this way you will be able to find out the network delay in the anywhere. So basically what you have to do is, if the sample value packet is navigating through multiple switches, you take a connection from BNET and loop it through all the switches in the network and bring it back to the um, this other port of the BNET. So that way you can exactly measure the packet delays. So individually or in a group, you can connect and determine the packet. Now let us go back and find out how you will advance or delay the packet intentionally. So I'll stop the monitor and I will stop the publisher as well. And here in the tools properties, you have a parameter to, in the publisher side, you will see a property, the compensate delay. So here I have set it as 130 because right now there is a packet processing delay within the BNet as 130 microsecond with respect to the local clock. So that's why I set it as, so there is always a overhead of for the processing in BNet of around 130 microsecond, and that's what we are trying to compensate here. That's why you see it as a um, you know uh, 1 microsecond delay in BNet. So if you increase this further, you will see those delays appearing in the actual subscriber. So subscriber will log the packet with the local timestamp, and it will, but publisher side, there's a delay. So if you reduce this by 50, right? So here instead of 130, if we like change it to 100, you will see an additional 30 microsecond delay. So instead of 130 minus 130, I am making it minus 100. Basically we are you know uh, making the packet go later. Oh, sorry. Yeah. So basically we are introducing a delay of 30 microsecond from the BNet perspective. So now let us click the OK. So you can tune this parameter based on how BNet behaves in certain scenarios, like based on the number of streams that you need to simulate. It will introduce some additional delays, and you can fine-tune or calibrate your loopback performance using this parameter, and you can also introduce additional delays as you like. Now let us run the publisher, and we will also run the subscriber. So I had changed the delay by 30 microseconds. So you can see that 30 microsecond delay was introduced, and additional 2 microsecond delays the processing of the BNET, and further we have additional 2.5 microsecond delay introduced by the switch in the network. So here you are basically intentionally delaying the packet based on the parameter that you configure. You can also advance the packet, like if you increase the negative value, you'll be able to uh, publish the packets earlier than you need, so that way you'll be able to simulate the completely out of sync device scenarios. So you can kind of advance the packets or delay the packet as you like. So based on the local clock, VNet will adjust the publisher and get the packets out. We are running out of time. I think we finished most of the topics that we wanted to present, and this is the last point. I will talk about the features that are planned in 2.4.0. This will be coming in June. We will be extending the verify IED feature to sample value. Right now, we only have GOOSE and reports covered, and also the MMS data model and datasets covered in client mode. We'll extend that to sample value in the next version. And we will also have the fault simulation capability in BNET. Right now you will have to simulate the RMS and angle manually. So manual simulation will be applied in the next iteration, and you can kind of simulate the basic data changes even in the current version, but in the next version you'll be able to simulate a fault, like using an exchange. You'll be able to specify the values, and you can simulate an actual fault in the network. And the last point would be the real-time visualization of RMS and phasor. Right now we are seeing everything in textual displays. Here, if you notice, we are seeing the RMS and angle values here. In the next version, we will have a visualization for the RMS and angle changes. So these are the changes planned in the next version. Okay, I see some questions from audience here, so maybe it's a good time to mention about all the discussions. So we have covered all the topics that we wanted to cover during the webinar, and let us go back to the questions. We'll try to address as many questions as we can and wind up at 9:50. So the first question I will see is that can client verify the reports? So in this scenario right now, the verification of report and GOOSE is only done in monitor mode, but in the next version, we will extend that capability to client as well. So that means client will be able to enable the report and further verify all the parameters between client and server, and also verify the report. So that capability will be added in the next version. As I mentioned, the sample value verification also will be available. So the client can verify everything, including sample value, plus you have the monitor mode verifying the sample value in addition to report and GOOSE. And as I mentioned earlier, we will also have the dataset node coming under the report and GOOSE, so you will be able to easily visualize the problems in reports and GOOSE. Other question I have is that the BNET. So why you have that negative delay pre-configured in BNET? So right now in the BNET, we have on the publisher side, we have a overhead of 130 microsecond approximately. This might change, as I mentioned, this might change based on the network scenarios and number of sample values published. So to tweak the delay introduced by the publisher, we can use this parameter. So that means the BNET can advance or delay the packets by that interval, and based on the loading within the BNET, you will be able to adjust that delay. So by using a calibration method that I shown you between publisher and subscriber with a physical cable connected between these two ports, you'll be able to find that correct spot, and further you can go ahead with the network testing. Yeah, the next question I see is that uh, how many sample value can be simulated in BNET. So right now we are focusing on troubleshooting the network. So that means you'll be able to simulate in the range of uh, 3 to 4 sample value streams in the network. Yeah, that's what we are targeting. So if you have any problems in the network, you can hook the BNET hardware and look at all the sample value streams that you have problems. You can select the respective devices from the SCD file and start looking at those sample value streams rather than selecting all. Yeah, I think we are already at 9:52, so we consumed around 7 additional minutes. Sorry for the delay. I hope this webinar was useful to you in understanding the new capabilities of Test Set and our future direction, and like all the future roadmap features as well.
Great. Yeah. Thank you so much, Taran, for this very informative webinar. And thank you everyone for attending this session. As always, if you have any questions, feel free to write to us. So these some of the email IDs, or even at marketing@calcitech.com. You should be getting a recording of this webinar in 24 hours time. If you have any questions also further, you can just reply to that email ID as well. We'll be happy to answer that. All right. Thank you so much, Steren. Thanks once again. Everyone,
Okay,
have a
thank
good
you.
day.
Thank you, everyone.